Okay, so this is, for real, our final lecture on group theory. There is a whole lot more that we could have done here. It's its own branch of mathematics, but I wanted to get through the major theorem at the end of this lecture before we move on to elliptic curves. So the first portion of today's lecture is on taking the product of two different groups. And then once we work through that, we'll be able to come up with a fundamental theorem the same way that we have a fundamental theorem for factorization of integers. So the idea for the product group is that we are going to take two different groups that we already understand, and we are going to glue them together. So you can actually think of this as the opposite of the quotient groups from last week, where I'm taking a very large group and I'm sort of dividing out one of its subgroups to make it smaller and easier to work with. That's the reason why these ideas have opposite names from each other, product and quotient. So I'm going to need some ingredients to make a product group. I'm going to need two or more groups. I'll just work with two for now. My groups are going to be called G and H. And because these are potentially different groups, they could have potentially different operations. So I'll use star G for whatever the operation of G is. Maybe this is addition, maybe this is multiplication. And I'll use star H for whatever the operation in H is. Maybe it's multiplication instead, or maybe it's addition instead of whatever we have in G. Or they can be the same. The product group, G times H, or G cross H, is a set which contains pairs, ordered pairs where the first coordinate is an element in G, and the second element is something from H. So technically, we already saw this last week with the wallpaper group when I talked about the integers z squared. Only there I presented it as vectors, but a vector is just a different way of writing ordered pairs. This is also how we saw the group of order 4 at the very beginning of the group theory unit. That is a product group as well. So these are what all my elements look like. That's half of the picture when we're describing a group. I also need to explain how to combine such things. What is the operation I'm going to use here? So let's say I have two different pairs. One of them has the name G comma H. The other of them has the name G prime comma H prime. And I want to be able to combine them in some way to get another element of the product group, G times H. So the idea is similar to the way that we work on ordinary vectors. We're going to take the first two coordinates. Both of them are members of the group G, which means that G star G prime is a valid thing to calculate, right? They belong to the same group. So we'll combine the first coordinates from both pairs to get the new first coordinate. And that'll be using star G. The second coordinates, H and H prime, both belong to the group H. So they form a valid combination as well, even if this is some different group operation, right? Star G could be plus, star H could be times, and we'll still get a valid answer for adding the G's together and multiplying the H's together. So this also tells us what the identity element of G times H has to be. It's going to be the identity element from G. That'll be our first coordinate. And the identity element from H will be the second coordinate. So this ordered pair becomes the identity element of G times H. Okay, so that is the strict technical definition. Let us take a more concrete example. So let's pick two groups that we're a bit more familiar with. We've been working with these for a while. So my group G is going to be the integers mod 2, right? Residues mod 2. We know this is a quotient group, but we don't need to worry about that terribly much right now. It's just a group that we know how to add inside of. And my group H is going to be the integers mod 3 instead. So my product group is going to consist of ordered pairs where the first pair is some residue taken mod 2, and the second element of the pair is some residue taken modulo 3. That is a little bit different, but I want to raise the question, could this different looking group actually be something that we've seen before? And of course, you know, because I'm framing the lecture this way, that's a loaded question. Let's start out by figuring the size of this product group. How many elements are in the integers mod 2 cross the integers mod 3? So if you think about what the elements of this group have to look like, the first coordinate comes from integers mod 2, and there's two different options. The second coordinate comes from the integers mod 3, and there's three different options there. So if I have two options and three options respectively, that means I've got 6 different ordered pairs. And in general, this will work for any product of finite groups. The number of elements in G cross H is just equal to the number of elements of G times the number of elements in H. So on the left side of my equation, in the parentheses is the name of a group. On the right side of the equation, I've got two different integers which are representing the sizes of two different groups. And this is just normal multiplication. I'm still using a dot for. So the group that I'm investigating has 6 elements, and here I've listed them all out. I've got 0, 0, 0, 1, 0, 2. Those are all of the ordered pairs that can start with a 0. And then if you don't start with a 0, you have to start with a 1. That gives me the ordered pairs 1, 0, 1, 1, and 1, 2. So these are the elements of this particular product group. Let's zoom in a bit closer and take a look at this element 1, 1. I know that 1, 1 comes from this finite group, right? There's only 6 elements. So 1, 1 can only have finite order. You only get infinite order elements when you have an infinitely sized group. So let's see if we can figure out the order of 1, 1, right? First I say, well, 1, 1 is not the identity element because I know the identity element of this group is 0, 0, right? Identity from Z mod 2, identity from Z mod 3. And this ain't it. So let's combine 1, 1 with itself. In the first coordinate, I've got 1 plus 1. And these are residues modulo 2. So that gives me a 0. In the second coordinate, I've got 1 plus 1. But this time, these are residues modulo 3. So I get a 2. So this element plus itself gives me 0, 2. Let's keep going, because I don't have the identity yet. If I take 0, 2 and I add to that another 1, 1, In the first coordinate, I have 0 plus 1. And again, those are residues modulo 2, so that gives me the residue 1 as a result. In the second coordinate, I have 2 plus 1, which is 3. And in the second coordinate, I'm using the integers modulo 3, so that gives me a 0. Now, I'm not going to spell this out the rest of the way, but you can see if I take my 1, 0 and add on another 1, 1, I get 0, 1. Okay, that's still not the identity. Add on another 1, 1, I get 1, 2. And then 1, 2 plus 1, 1 gives me 0, 0, which is my identity element. So this means that the element I'm investigating, 1, 1, it has order 6. So this product group is generated by 1, 1. That was the vocabulary I was using in my lecture last week. The more practical side of this is that every single element in the product group is just some combination of copies of 1, 1, all just stuck together, right? I have all 6 of them shown in these equations here. So this group is a cyclic group, and it contains 6 different elements. So as we were seeing with the cyclic groups last week, that means it should behave like some other cyclic group we have already seen. And I will be right back with that thought in the second part of this video.